All right, so today we are going to look at transitive closures. Okay, so what is a transitive closure? So essentially, if you want to know that A can go to B and B can go to C, then there is a path from A to C as well, right? So essentially, you want to know that what are all the vertices that can be reached from each vertex. Okay. So what we're going to do is we're going to use Floyd's algorithm. Okay, so Floyd's algorithm is actually for all pair shortest paths, right? So if you want to know the shortest path from every source to every destination, right? You can use Dijkstra's for that also, but Floyd's algorithm is more efficient, right? So we'll talk about this algorithm, okay? And we'll see how Floyd's algorithm works for all pair shortest path, and then we'll just map it to transitive closures, okay? Just by changing the operations, it can give you the transitive closures. All right. So let's start with the all pair shortest path problem, right? And how Floyd's algorithm works for that. And then we'll come to transitive closures. So how does Floyd's algorithm work? We'll need a definition, right? Let Pij of k denote the minimum weight path from I to j that only comprises of v1, v2 up to vk as intermediate vertices. All right. So essentially it's the shortest path. So if let's say this is your I, this is your j, this is the path, the shortest path from I to j, where the vertices only come from the set 1, 2 to k, right? Not necessarily in the order. So it's just that the intermediate vertices, not including I and j, the intermediate vertices can only come from this subset of vertices, right? v1, v2 to vk. So maybe v1 comes here, maybe vk comes here, maybe v10 comes here, and so on, right? Okay. So is the definition clear? So that's Pijk, right? And let us also denote Dijk as the corresponding weight of the path, right? Okay. So that's the distance. That's the shortest path distance from I to j, comprising only of vertices v1, v2 to vk as intermediate vertices. Okay. So how can I derive Dijk if I have all the information up to, let's say I have all the Dij's up to k minus 1, right? For all ij's. If I have all this information, how can I figure out what is Dijk, right? So there are only two cases. Let's consider the path Pijk, right? The shortest path from I to j, passing through v1 to vk, right? Either it includes vk as a vertex or it does not include vk as a vertex, right? So either vk is in Pijk or it's not. First, let's look at the case when it's not in Pijk, right? So in that case, what will happen? Well, that means that Dijk would be the same as Dijk minus 1 because vk was not in the shortest path of Pijk. So vk does not appear on the shortest path. So basically, it's shortest path from I to j only passes through vertices v1 through vk minus 1. Well, the shortest path which is allowed to pass through v1 through vk actually does not use vk and only uses the vertices v1 through vk minus 1. So therefore, in that case, dijk will be exactly the same as dijk minus 1. Yeah. And what if actually vk appears in this path, as in this example, right? If vk appears in this path, then I can say that dijk will be equal to, well, there's a path from I to k. Well, what are the intermediate vertices? All the other vertices other than vk are coming from the set v1 through vk minus 1. So the path from I to k, vi to vk, sorry, this should be vi, vj, right? Yeah. The path from vi to vk will only comprise of vertices coming from the set v1 through vk minus 1, right? And similarly, the path from vk to vj will only comprise of vertices coming from the set v1 through vk minus 1. Okay, so I can write this as vkj k minus 1, right? So basically, if I take the min of these two, that tells me what is the shortest path from I to j comprising only of vertices v1 through vk. Is that clear? Any doubts with this formulation? All right. So that's Floyd's algorithm. And now, how do you get the final answer? Well, once you compute dijn, you're done. Dijn means what? It means the shortest path from I to j passing through vertices v1 through vn. That's all the vertices, right? So that is actually the shortest path that can possibly be there. And what's dij0? What will dij0 be? Anyone? How do I initialize this? So if there is an edge between I and j, then it is the weight of the edge. Otherwise, it is infinity, right? Infinity if ij does not belong to the edge set and equal to the weight of ij if ij belongs to the edge set. Right? So this does not belong. Okay, so now let's write the sequential algorithm for Floyd's, right? It's quite straightforward. Once you have understood this. So this is Floyd's sequential algorithm. What do I have as input? I have the adjacency matrix A. The adjacency matrix stores the weights, right? And now what do I do? So I'm going to denote this entire matrix, which has entries dij k. I'm going to denote it by d of k. Okay, capital D. So I have d0 is equal to a. So the starting point is just the original weights, right? That's what we just saw. Yeah, except that, set infinity if does not belong to E. Yeah. So in the adjacency matrix, you might be storing that as zeros, right? So you just have to replace that with infinities. Then what do? I have to compute this D matrix in iterations, right? The K increases. I start with D0, then I'll compute D1, right? That's how this works if you look at this recurrence, right? Dijk is computed from entries coming from Dij K minus 1, right? So dk will be computed from dk minus 1. Yeah. So I'll run this loop for k is equal to 1 to n. Yeah. And I'm going to compute dk in this loop, right? In one iteration. How do I do that? So I have to look at every entry and update it. For I is equal to 0 to n minus 1. For j is equal to 0 to n minus 1, right? And what I'm going to do is I'm going to update dij k. How do I update dij k? It's simply min of dij k minus 1 and dik k minus 1 plus dkj k minus 1. Yes? That's it. That's Floyd's algorithm.
Given this
Done.
setting, shouldn't our vertex number start from 1?
Shouldn't vertex number start from 1?
1
Why?
to n instead of 0 to n minus 1. Because I mean, our base case is that it's dij 0, so all the vertices, basically, I don't have any intermediate vertices.
That's a good point. So what is D0? I already have D0. When I want to compute D1, I want to look at vertices. V0 can be an intermediate vertex, right? That's what you're saying. Yes, you're right. Let's start the vertex numbers from 1, right? That's important. Yeah, is that fine now? Okay, good. All right, so that's Floyd's sequential algorithm, right? And what is the time complexity? Well, straight away, there are 3 loops running from 1 to n. So it's clearly theta n cube, right? The update operation is just a constant time operation. And what's the space complexity? How much space do you need? Theta?
N cube.
N cube. Can you do better?
Can make do with 2n squared matrices.
Yeah, so you
maybe.
can do with theta n square because you only need the k minus 1, right? You don't need k minus 2, k minus 3, right? And so on. So you can do with theta n square. I hope it's clear, right? This adjacency matrix A is of size n cross n.